Good morning. Today we are doing our second homework assignment on energy and why reactions occur. And this assignment is on collision theory and equilibrium. So here we go. The first question is asking about catalysts and how catalysts work. So if you'll recall your energy diagram has energy on this axis and reaction on this axis. And you're going from reactant to product, and this piece here, that is your energy of activation. That's what it takes to get started on your reaction and to get to the product. So what does a catalyst do? A catalyst is not used up in a reaction, it just makes it go faster. The way it makes it go faster is by decreasing your activation energy, because this difference directly affects the rate of the reaction. The harder it is to get over the hill, the harder it's going to be for the reaction to proceed, the slower it's going to be. So a catalyst just lowers the activation energy. And in this chapter we don't explain why, but if you go on to take the next class in the series, we go into a little bit more detail on how, for instance, biological catalysts can help decrease the energy of activation. Okay. We've got here an equation, and we want to know how making changes, what's that going to do to the reaction rate. So if we've got hydrogen and we add nitrogen and that goes to form NH3, usually increasing temperature increases the reaction rate. So if I decrease, I would expect the reaction rate to decrease. That's just collision theory. Basics of collision theory tells us that you have to have things collide with sufficient energy in order to react. So increasing the temperature increases the energy available and probably increases the number of collisions as well. That's why increasing the temperature usually increases the rate. Here this has to be done in the presence of an iron catalyst. If I remove the catalyst, well, we just talked about how catalysts speed up the rate of reaction. So if I remove a catalyst, I would expect the rate of the reaction to decrease. And finally, if I increase the amount of H2 gas I've got, then I would expect more collisions to occur. If I increase the concentration specifically, not just the amount. I've got a more crowded space, more collisions are going to occur. The more collisions occur, the more chances that collision is going to lead to a profitable reaction. So that would increase the reaction rate. All right, next we're looking at equilibrium constants, and the equilibrium constant is the product divided by the reactants, and each of these is raised to their coefficients. So the equilibrium constant for this guy is going to be CH3OH on top in the numerator, and CO on the bottom in the denominator, and H2, but it has to be squared because there's two of them, in the denominator. So these ones would not be used. Okay. And equilibrium constant expression can be rearranged to solve for any of the variables. If I rearrange the one that I just did for the methanol, all right, here, this is what we came up with. They're just asking us to do a little bit of algebra. So K is CH3OH divided by CO times H2 squared. Now if I do a little bit of algebra, what I'm going to do is multiply both sides by CO and H2 squared. Apply that by CO, H2 squared. And what if I do that? Those cancel. And I find that K times the CO concentration times the H2 squared is equal to the CH3OH. You guys should be able to do this pretty easily. This is just simple algebra. So that's the one. Suppose that the molar concentrations are these, then find out the concentration of the CH3OH. All right, I just plug it in. I know that K is 2.3 times 10 to the fourth. Okay. They're telling me that the CO is 0.02 and that the H2 is 0.08. And that's squared. So we just plug that in. 2.3 times 10 to the 4th. Multiply that by 0.02 and multiply that by 0.08 squared. And I get a concentration of 2.944. And since these were given in molar, capital M, and this is going to be capital M as well, it's important to note that the equilibrium constant K is unitless, and you're just going to maintain whatever those concentration units are. Excellent. Now consider a situation in which we've got all of these and they're all 2.2 molar. What statement best describes what's going to occur? Well, as you can see, because K is very large, that means that products are favored over reactants, because in our K expression, products go on top, reactants go on bottom. So if K is very large, then that means that the amount of products is much higher than the amount of reactants. And you can see that here. If these were 0.02 and 0.08, then this was 2.9. So clearly the products, the amount of products at equilibrium is much higher than the amount of the reactants for this particular reaction. So if they're all the same, then it's definitely not at equilibrium, because at equilibrium we're going to have more methanol. So the reaction is not at equilibrium, and it's going to proceed in the forward direction until I get a lot more of my product, until equilibrium is reached. So the answer is the forward reaction is favored until equilibrium is reached. Excellent. Next, write the equilibrium equations for the reactions and tell whether reactants or products are favored in each case. For the first one, because K is so tiny, I'm sure that the reactants are favored. And for the equation, it's going to be H2S squared on top, divided by S2, and divided by H2 squared on the bottom. So it looks like that one. Next, because K is greater than 1, I know products are favored. I can go ahead and answer that one. And I think this is the one we just did, right? CH3OH on the top, CO on the bottom, and H2 squared on the bottom. Being able to write equilibrium equations will definitely be on the test, as is being able to do math with these. Again, because K is greater than 1, I know that products are favored. And for the expression, we have BrCl squared on top, and Br2 and Cl2 on the bottom. Neither of those are squared. Last question, because K is very small, remember that's 0.0068 because of the exponent, I know that reactants are favored. And this should be I squared, because of the coefficient, divided by I2. There we go. Next here, they ask what K is, so we have to come up with the K expression ourselves and then plug in these values. So K expression is going to be NO2 squared divided by N2O4. That's K. And since the NO2 is 0.0325, and that's squared, divided by N2O4 is 0.147, I can plug those in. get a K value of 0.00719, or 7.19 times 10 to the minus third. If I put that in scientific notation, either is appropriate. Okay, this is the same thing, except now I'm going backwards. If I know the K, can I calculate one of my original concentrations? Of course, because I can do algebra. And so could you. I know you can, because it's a prerequisite for this class. So even if you're feeling shaky, I know you did it once before. So K is CO2 squared, because there's a 2 in the coefficient, divided by my CO squared and my O2. And the K is 1310. All right, calculate the O2. That's this one. If I want to calculate O2, I'm going to multiply both sides by O2, divide both sides by 1310. And I'm going to find out that the O2 is the CO2 squared divided by the CO squared divided by 1310, right? Because I divided both sides by 1310. And then I multiplied both sides by O2. And that got O2 by itself and on top, which is what I wanted. Okay. All right, so if the CO2 is 0.018, and the CO is 0.0201, and we get 1310 here. Can plug those in. Notice I hit divided by 1310 and not multiplied by 1310, because if I hit multiply, then it's going to move the 1310 to the top. 6.12 times 10 to the fourth. Negative fourth specifically. Did I square the other? Let's try this. Oh, I'm sorry. 0.18. I'm off by a factor of 10 here. Look at that. Terrible. The decimal point goes right here. That's what I get for transcribing that top number incorrectly. So 0.18 squared divided by 0.0201 squared and 1310. There we go. 0.0612. Much better. Okay. Now if I want to calculate the CO2 instead, given these values, that's fine. I could rearrange this equation for the CO2. In this case, I'm just going to multiply both sides by the CO and the O2. My equation is going to look like this. K times the CO, which is squared, times the O2. That's going to give me the CO2 squared. Ooh, but if they want the CO2, then I'm going to have to take all of that and take the square root, because the square root and the squared are inverses. So that's what's going to get rid of the squared part for me. Okay. What do I plug in? 8.1 times 10 to the minus 2. So we get the square root 1310 times 8.1 times 10 to the minus 2 times 0.0521. It's going to give me the CO2. $13.10 times 8.1 times 10 to the minus 2 times 0.0521 and take the square root of that. There's the square root. I get 2.35. I'm sorry, look at that. I did it again. 0.521, 0.0521. Look at me. That's terrible. Off by a factor of 10. I can't manage to get this decimal in the right spot. Glad I noticed that before I put the answer in. Let's try that again. 1310 times 8.1 times 10 to the minus 2. Multiply that by 0.521. Take the square root of that. There we go, 7.43. Oops, what did I do wrong this time? Let's look at our equation. We've got the K here, CO2, oh goodness. It's supposed to be squared. And then the O2 here. Okay. I hope watching me make mistakes helps you not make the same ones. And that whole thing is going to be squared. Multiply that by 0.521. And then take the square root. 2.11. Let's try that. There we go. Always make sure, because really all of this chapter, all of this section is simple algebra, but you have to follow the instructions, right? If it tells you to square it, you have to square it. If they tell you they've got this much, then that's what you need to plug in. So a lot of students will like this better than the dimensional analysis because it feels like there's rules, and if I just memorize the rules and follow them, you'll get the right answer, which is true. Dimensional analysis feels a lot more nebulous, and I can understand that, but you do have to stick to those rules, which I was not doing a good job of. Okay, so definitions. Process or reaction which consumes heat, that would be endothermic. Releases heat would be exothermic. Negative delta G is spontaneous or exergonic. Positive would be non-spontaneous or endergonic. If the rate of the forward is equal to the rate of the reverse, that would be equilibrium. Doesn't mean nothing's happening, it just means that both the forward and the reverse are happening at the same rate, which means the amount of energy invested to get it started. Yep, that's activation energy. Excellent. Okay, so we're talking about reactions at equilibrium, and what would the constant K be for this reaction? We already know how to do this. Let's clean up our plate. And looking at this equation, so I've got SO3 squared divided by SO2 squared times O2. That's going to be K, right? That's what it says here. And then they give us values. SO2 is 0.48. This is 0.4. And this is 1.12. And they want us to calculate K. All right, I can plug that in. I'm good at this. 1.12 squared divided by 0.48 squared and divided by 0.4 gives me a K of 13.6. Okay. Now I'm going to disrupt the equilibrium by increasing the amount of SO2 here. I'm going to almost triple it, essentially, increasing the amount of reactant. So calculate the new ratio of products to reactants, assuming that we haven't yet reached equilibrium, so I'm going to plug those in the same way. The SO3 for the moment is still 1.12. It's still squared. Divided by the SO2 for the moment, they increased it to 1.48. That is still squared because there's coefficient there. And the O2 is for the moment 0.4. So that would give me 1.43. All right, so when the concentration is increased, the ratio of products to reactions shifts. In what direction will the reaction move to regain equilibrium? Well, a higher number indicates a higher ratio of products to reactants. So since now I have a lower number, we know we want to regain equilibrium. We're going to move towards making more products because we need to reestablish this number that has a higher ratio of products to reactants. So we're going to move towards the products. Okay. And mathematically, you can see why that would be. All right. So here we go, looking at this with regards to Le Chatelier's principle, which says if I disrupt something that's at equilibrium, I'm going to try to reestablish that equilibrium. And what we see is if I decrease the volume, then there's less space for gases. And here I've got 1 mole of gases, 1 mole of gases, goes to form 1 mole of gases. So 2 moles of gases on the left, 1 on the right. I have less space for gases. So I'm going to move towards products because there's less gas molecules that need space, that take up space in that case. And the increase in volume would do the opposite, increase to reactants, because I've got more space for my gases on the reactant side. So if I increase the volume, then I've got more space for those to form. Adding a catalyst doesn't change where the equilibrium lies, it just makes the reaction go faster. So it might make it reestablish equilibrium faster, but there's not going to be any shift towards reactants or products. If I add chlorine gas, that's adding a reactant, then I'm going to get more of my PCl5 products. That's one way that we reestablish equilibrium, by consuming what was added and making more of the thing on the other side. So that's going to shift towards product. And if I remove the phosphorus trichloride, that's PCl3, that's removing a reactant, then I'm going to shift towards the formation of reactants so I can make more of what I removed. I'm offsetting that change by refilling that hole that I made, essentially. So I'm going to shift to reactants. Okay, this is very... Here we're not using math, we're just kind of using the logical thought process to explain kind of what's going to happen. Okay, so here we're going to say we're going to increase the pressure. What happens? If I'm talking about pressure, then you're going to look at gases and see which side has more space or needs more space, right? Because gases take up a lot of space. So here I have 2 moles of gases. Here I have 3 moles of gases. So 3 moles of gases take up more space than 2 moles of gases. Increasing the pressure says I have less space. So I'm going to go to whatever side has fewer moles of gases. So there's a concentration of the products that will decrease because I'm going to go backwards to make more reactants. In this case, I've got 1 mole plus 1 mole makes 2 moles. So I have 2 moles on the left, 2 moles on the right. Changing the pressure doesn't have any effect on this reaction because I have the same number of gas moles on both sides. And here I have, we ignore this because it's a solid. 2 moles of gases going to form 1 mole of gases. So if I have less space for gases, I'm going to move to the side that has fewer gas particles. So my reactants, or sorry, my products increase. Okay. That's the direction I'm going to move. All right, and now here's one. Here is a reaction where we're looking at concentration. So these reactions are occurring in solution. And I've got iron 3 plus chloride makes this iron 3 chloride complex. Okay, it's a polyatomic ion. So if I had iron 3 nitrate, that's what's happening here. I want you to notice the nitrate is not really involved. You can just ignore the nitrate, but note that this is in fact an iron plus 3 ion, as evidenced by the fact that nitrate has a -1 charge and there are 3 of them. So I'm adding this guy to the solution if I add iron 3 nitrate. So if I add a reactant, then I'm going to get more products. So it's going to increase the equilibrium concentration of that product there. If I precipitate chloride by adding AgNO3, essentially, again, the nitrate is doing nothing. It's just a spectator. It's not involved. But precipitate is because chlorides are not soluble with silver. So I'm going to form silver chloride solid. So I'm removing chloride from the reaction solution. That's what this is doing. It's removing chloride. So if I remove chloride, then this whole reaction at equilibrium is going to shift to the left to replace chloride that was removed. And by doing so, it will decrease the amount of the product, FeCl2+, that's in equilibrium. Okay. If I increase the temperature, that might make the reaction go faster, but additionally they tell us it's endothermic, which means it absorbs heat. You could think of this as saying heat is a reactant because I use it up when I go to form the product. So if I increase the temperature, that's like adding more heat or adding a reactant, so I'm going to get more of my product here. And finally, catalyst does not change equilibrium concentrations. It only changes the rate at which those are achieved. Okay, next question. This is the same as the endothermic one that we just looked at. Let me write this out. Might make a little more sense. I've got carbon plus water goes to form CO plus H2. And they tell me that the delta H is 31.3 kcals per mole. And again, that's as this reaction is written. Because that's positive, I know that this is endothermic and that the reaction absorbs heat as it moves forward. So reaction is, this is like, it's a reactant. I could say carbon plus water plus 31.3 kcals of heat will produce carbon monoxide and water, or not water, but H2. So I could just put that right into the reaction itself, because that's essentially what this is saying. I could either say I have this reaction and this is the amount of heat that's involved, or I could say in this reaction I absorb this amount of heat in order to make those products. It's the same thing. But if I put it inside of the reaction like so, then it helps me see how the equilibrium could change if I add or remove heat, because I could treat it just like any one of my other reactants. So here, if the temperature is decreased, then I'm removing heat from the reaction. I'm removing heat. And so if I remove a reactant, then I know equilibrium tells me that I'm going to try to offset that change by making more of that reactant. Therefore, I'm going to move the reaction this direction. They want to know how much the H2 changes. Does it go up or does it go down? Well, if this is my H2 and I'm moving that direction, then I'm removing it, right? So that is being decreased when the temperature is decreased. Okay. And finally, which statement about the system is not true? Let's see, we've got two SO2s with one O2 going to form two SO3s plus heat. So they're telling me that this is exothermic because I'm evolving heat. And they tell us the K value, which is very large, so we know that products are favored. So heat is a product and products are favored. Okay. So let's see, at equilibria, SO3 is a predominant substance. Yes, because products are strongly favored. Large value of K means reaction goes essentially to completion, yet you'd be hard-pressed to find either of these two in the reaction mixture. Removing O2 would cause an increase in the amount of SO3? Probably not, because if I'm removing a reactant, then I'm going to go to form more reactants. So this is a possibility. Let's see. Adding SO2 would cause an increase in the amount of SO3. Yes, because adding a reactant offsets that to form more products. And I skipped this one because I wanted to come back to it. Heating the system would cause a breakdown of SO3. Yes, because heat is a product. So if I add more heat, I'm adding more product, so it's going to push the reaction backwards, which breaks down the SO3. So this is the one that they want. Okay. That's how we look at Le Chatelier's principle. I hope that was helpful, and I hope you all have a great day.